The next thing that we're going to look at is the way that nucleotides come together to make a nucleic acid. Remember, in the last section, we talked about how a nucleic acid is simply anywhere from thousands to millions of nucleotides connected together. We didn't talk about how they connect together, and that's what we're going to do in this section. The nucleotides connect together in what we call a phosphodiester bond. It's also called a phosphodiester link or a linkage. And they connect together to make a nucleotide. And again, to make a nucleic acid. I want to draw a parallel between this and proteins. Proteins are amino acids connected through peptide bonds, and nucleic acid is nucleotides connected with a phosphodiester bond. I see that I really spelled phosphodiester very wrong. Phosphodiester. So let's talk about this phosphodiester bond and how it works. The phosphodiester bond is a connection between one of the OH groups of, we're going to say, nucleotide number 1 and the phosphate group of nucleotide number 2. So let's draw two. We're going to start by drawing 2 nucleotides, and we're going to draw them a little bit more abbreviated than in the last section because we don't really need to see all of the different hydrogens and things like that. So over here, we're going to draw the nitrogen, and we're just going to make, it's standard to just kind of make a rectangle to represent the base that's hanging out over there. And we're going to be drawing DNA. So we're just going to draw in the OH group. We're not going to draw any of the hydrogens that are on the monosaccharide part. And then up here we have the CH2 with our phosphate. I am going to draw the phosphate group all the way out. Remember, 2 of those oxygens have negative charges on them. When 2 nucleotides come together to make a nucleic acid, one of the points of connection is the OH group on the sugar. And then the other point of connection is going to be the phosphate. So when I draw my second nucleotide, I'm going to draw it underneath like this. And I'll explain to you in a minute why I just moved that double bond to the phosphorus, why I just moved it around a little bit. So I'm drawing my second nucleotide down here underneath it. And I'm just going to draw the same nucleotide, some sort of base out here. We're going to represent that with a rectangle and the OH group. So nucleotide number 1 is going to be using the OH group on the ring for the phosphodiester bond, and nucleotide number 2 is going to be using its phosphate group to form the connection. And the reason that I switched places, so this particular carbon or phosphorus oxygen double bond, which is traditionally drawn sticking up, when a linkage is formed, when the phosphodiester link is formed, it is actually formed between one of the double or single bonded oxygens. And so I've reoriented that phosphate group to make it easier for you to see, to visualize how they come together. So these 2 nucleotides are going to add together with each other, and they are going to end up producing. I'm going to try to use my sweet cutting and pasting skills again. And what I'm going to do is just modify this structure. Let me kind of shorten my arrow a little bit. And so what we're going to modify is this area of the ring. So the OH group goes away, and the oxygen of the phosphate group is now directly connected where that original OH group was located. We still have a negative charge down here. I realized I forgot to draw the negative charge in up there, so we'll fill that in. So that one of the oxygens in the phosphate group still has a negative charge on it, but the other oxygen is now being used to form a bond with the other sugar. So it looks like this. The phosphodiester link is this right here. And that's the point of connection. And then if we wanted to bring a third into this particular structure, it would get added right here at that spot, and so on. So in addition to stacking vertically, they end up making kind of a zigzaggy, almost like a set of stairs pattern as they go down the chain. Now this, as you can see, this is a really cumbersome drawing, and so when we are attempting to draw a nucleic acid, like if we want to draw it out, not abbreviate it with a formula, we have a shortened way of drawing this structure. So if we want to represent the structure of a nucleic acid in a faster way, we are going to draw the sugars as their 5-membered rings like that. And then instead of drawing the full-on phosphate group, we're going to draw this notation right here. So first of all, this, which is using line notation like we learned in organic chemistry, that is a carbon. That is this carbon right here, right there. And that P, typically drawn in a circle, that is representing the phosphate group. So that's just a way of shorthanding this whole entire group rather than drawing all of it out. So that's nice and easy. And then for the base, we'll again use the rectangle or box notation. And a lot of times people are going to actually write the 1-letter abbreviation of the base that's attached to that particular spot, to that particular ring. And so if we wanted to draw a full-on nucleic acid, and we wanted to draw the next guy, this is the point of connection. We would have a phosphate group that was making the connection. There would be a CH2 connecting to sugar number 2, and that sugar number 2 is going to have some sort of base on it. We'll make that base A, and let's go ahead and add one more on here. So you can see this is way faster. Still, you know, a little bit tricky because of having to draw the 5-membered rings. We'll make that base T, so this is a cat. And then if this was a full strand of a nucleic acid, and this was the very end, we would need to have an OH group down here to signify that that's the end of the strand. So there's an OH group down here because this is the end. Of the nucleic acid. The ending of the nucleic acid, so this is an end up here as well. This would be the top and the bottom. This is also an end, or maybe the beginning. The endings of a nucleic acid are indicated by the numbering system that we would use when we were numbering monosaccharides way back a long time ago, when we were first learning about monosaccharides and learning how to roll them up and turn them into their cyclic forms. You learned the numbering system that is used with a monosaccharide. So you learned that the very right-hand point carbon is going to be carbon number 1, and then you continue around the ring clockwise like this. 1, 2, 3, 4, 5, and we would continue extending that numbering outside of the ring as well. So the notation that we use for the beginning and the end of a nucleic acid is that we say that up here on the top, we call this the 5' end. That apostrophe looking symbol is pronounced prime, so we would call this 5' and that is referring to that carbon number 5 right there. And then down here, this particular end, we call this the 3' end. Again, that's pronounced 3'. And why is it a 3 and not a 1? Well, it's referring to this being the end. The OH group is the end, which is attached to carbon number 3. So the 5' end and the 3' end represent the beginning and the ending. The 5' end is the beginning of the nucleic acid, and the 3' end is the ending of the nucleic acid. When we write the structure of an amino acid, or it's an amino acid, when we write a nucleic acid in a molecular formula type notation, then we will always write it from left to right, 5 to 3. So if we're going to write in written form, we write from top to bottom, left to right. So top on the left and bottom on the right. Or another way of thinking about that is 5' to 3', left to right. So the 5' will be on the left and the 3' will be on the right. So for example, a lot of times people will actually write 5' at the beginning and 3' at the end, like that, 5' on the left, 3' on the right. And what we write to represent the components of the nucleic acid is just simply the 1-letter abbreviation for the base pairs. So this 3 nucleotide nucleic acid that we just drew, if we wanted to write it, we would just only have to write the 1-letter abbreviation for our bases, which is CAT. I left a lot of room there to fill it in, but the way that this is written is without spaces, everything jammed together. So there's no spaces anywhere in that notation. This is called the primary structure of a nucleic acid. The primary structure, just like the primary structure of a protein, the primary structure of a nucleic acid is just simply the sequence, the order from 5 to 3, the sequence of nucleotides.